In this video, we're going to look at two operations that we can perform on a vector field. These are called the divergence and the curl. Let's say that we have a vector field. So we'll call that capital F, and just to represent that it's a vector field, we'll put the vector symbol on it. And if we wanted to just talk about this vector field generically without going through all the details of what each component looks like, then symbolically we just call our components P, Q, R, like that. So P always represents the first component of the vector field, R represents the third component, etc. So based on that, we're going to write down the divergence of F. In symbols, we'll usually write div for short for the divergence. So we write div F like that. What this represents: partial derivative of P with respect to X plus partial derivative of Q with respect to Y plus the partial derivative of R with respect to Z. So you're taking all these partial derivatives, you're summing them up, and so what the output is here is just a function. We're going to look at our second operation, the curl, and then we can do an example where we practice both of them. So curl of a vector field F. In symbols, we'll just write curl F like that. To calculate the curl F, we think of this as a 3x3 determinant. We're going to put our unit vectors I, j, k in the top row. In the middle row, we're going to put these partial derivative operators. So we're going to write the symbols delta by delta x, delta by delta y, and delta by delta z. And then in the bottom row here, we write the components of the vector field. So the P, Q, and R, whatever functions those might be. So that's how we're going to set up curl F. Now let's jump into an example and we'll see exactly how to calculate the divergence and the curl. Here we have a vector field. We know what the three components look like, and based on that, we're going to find the divergence and the curl of F. Let's do the divergence first. So we write div F. General formula, we're supposed to take the partial derivative of the first component with respect to x, add that to the partial derivative of the second component with respect to y, and then add on the partial of the third component with respect to z. So specifically, we'd be taking the partial with respect to x of x cubed y squared z plus the partial with respect to y of x squared z, and then finally plus the partial with respect to z of xyz. For the first term here, partial with respect to x, that would look like 3x squared y squared z. For the second term, there's no y in there, so the partial with respect to y is just 0. I won't bother writing that down. And then partial with respect to z of xyz is xy. So in general, your divergence is just going to end up being some function of x, y, and z. Now let's try the curl of F. So in our definition above, we wrote down how to set this up, but here we're going to get a sense of what this is really giving us. So in our first row, we're going to write down our unit vectors, I, j, k. Second row, we're going to write down the partial derivative operators, so things like delta by delta x, delta by delta y, delta by delta z. And then in the third row, we're going to fill in our components of our vector field. X cubed y squared z, x squared z, and xyz. So now we can scroll down. We don't need to look up at the question anymore. And the idea is that we're going to compute this determinant. So we're going to do cofactor expansion along the top row. Remember, with determinants, there is an alternating sign pattern here whenever you do cofactor expansion. So we're going to have vector I times the following 2x2 determinant. I'm going to write down all the details just for a moment, and then I'll show you how we typically calculate this. So in thinking about this 2x2 determinant, symbolically, it looks like saying delta by delta y times xyz. But what we really mean is apply the operator delta by delta y to xyz. So we're letting this partial derivative operator act on this thing, and we're just taking a partial derivative is what's happening. And then we're going minus delta by delta z. Again, same thing. The operator delta by delta z is going to act on x squared z. And then we'd have minus j times some stuff, and then plus k times some stuff. So I write out this first step just so that we understand the meaning of what's happening when we multiply this operator with a function. We just mean take the appropriate partial derivative, right? So here's how we would normally do this. We'd say vector I times, now let's think about this little 2 by 2 determinant. So partial with respect to y of xyz is going to give us xz, and then we subtract off the partial with respect to z of this thing, that would be x squared. So that's what our first term looks like, and then we're going to do the same thing. We're going to go minus j times some stuff, and then plus vector k times some stuff. So let's look at this minus j term. So just imagine crossing out that row and column there to clean this up, and then we're going to do this 2 by 2 determinant here. Taking the partial with respect to x of xyz would give us yz. And then we subtract off the partial with respect to z of x cubed y squared z. So that would give us x cubed y squared. That's the j term done. And then finally looking at the k term, going to do this little 2 by 2 determinant. So delta by delta x of x squared z is going to give us 2xz. And then we go minus delta by delta y of this guy. So that would be 2 x cubed yz. The most important thing to notice here is that this is a vector. So when you calculate the curl of a vector field, what you're producing is a vector. We'll talk a little bit more about the physical interpretation of this vector in a few minutes, but for now we're just focusing on the calculation. So when you leave your answer, you could leave it in this form, or you could go back to the component form of a vector. So to get your x component, you're just looking at what's being multiplied with this vector I. So you'd have xz minus x squared. If you are going back to component form, just be aware that this j term is always going to have a minus in front of it, so there's going to be a sign change. It's going to be actually x cubed y squared minus yz in this y component, and then 2xz minus 2x cubed yz. So I would say either of these, either this one or that one, are good ways of expressing the curl. We're going to do a second example of computing divergence and curl in just a moment, but before we do that, I wanted to talk a little bit about notation. So let's recall the gradient vector. If we're talking about the gradient of a function, we would write del f like that, and what that represents is a vector that contains all our partial derivatives of f, so things like delta f by delta x, delta f by delta y, delta f by delta z. Now the idea here is that we can make sense of this del symbol on its own, and that's the notation that we want to introduce here. We're going to define this as the del operator. So in symbols, we just write this del symbol, and what it represents, it's a vector that contains a bunch of operators. So it contains the operator delta by delta x, delta by delta y, delta by delta z. The advantage of defining this del operator is then we have a quicker way of writing down the divergence and the curl. So if you want to talk about the divergence of a vector field, that can be written del dot f. So you're just taking this del operator and you're doing a dot product with your vector field. And that's going to let these different partial derivative operators act on the different components of f. Curl f can be written in a faster way as well. We can say that's the del operator crossed with our vector field, where this cross just represents our usual cross product. So let's try one more example of calculating divergence and curl of a vector field with this new notation in mind. So here we have a new vector field, and based on that, we're going to find del.f and del cross f. So let's start with del.f. Well, based on our previous discussion, if we were going to say this in words, we would say that's the divergence of f. If we were going to calculate this, well, if we just practice our notation, we would say the del operator is this vector that contains components like delta by delta x, delta by delta y, delta by delta z, and we're going to do the dot product with f, our vector field f. And if we wanted to just talk about f quickly and we didn't want to write down all the details, we'd say our vector field f looks like PQR. So when we actually perform this dot product, we're supposed to multiply the first components together. So we get something that looks like delta by delta x times p. But this is not actually a multiplication. This is letting the operator delta by delta x act on p. So a more natural way of writing that is actually delta p by delta x. And then the dot product sums up. We get three different terms. And in each case, we're just multiplying the appropriate components together. So you'd get delta q by delta y plus delta r by delta z. So sure enough, that's our familiar divergence. And this del.f is just a really concise way of writing that using the del operator and the dot product. So del.f, think divergence of f. And what that means is just take the appropriate partial derivative of the appropriate component and sum those up. So let's try it. First component, take the partial with respect to x, we'd have z cubed. Second component, take the partial with respect to y. Okay, we're going to have a chain rule. Derivative of sine is cos. So we're going to have cos xyz, but then times the derivative of the inside stuff with respect to y. So that would be xz out in front. And then finally, plus the partial of this third component here with respect to z. Well, there's no z in there, so that partial derivative is just going to be 0. So there we have our divergence of f done. So now let's try del cross f. So whenever you see these symbols del cross f, think of that as the curl of f. And let's make sense of this just from a notational point of view. So to calculate the cross product, we're going to use the method of setting up a 3x3 determinant. We write our ijk in the first row. We write our first vector in the second row. Okay, first vector is this del operator here, which has in its components delta by delta x, delta by delta y, and delta by delta z. And then in the bottom row, we write the components of our second vector, which in this case is our vector field. So if we wanted to just write this generically, just as a little formula for ourselves without caring about this specific vector field, we would just call the components PQR. So whether you see in words curl of f, or whether you see in symbols del cross f, think about setting up this 3x3 determinant. You've got ijk in the top row, you got partial derivative operators in the second row, and then you have your components of your vector field in the bottom row. So we're going to specifically try this calculation here, and we'll just fill in the components of our vector field. So they were xz cubed, sine of xyz, and then it was 2x plus 3y. We're going to expand this determinant along the top row. Remember, there will be alternating sign pattern as we expand. So let's see if we can do this the fast way. So we're going to have vector I times a certain 2x2 determinant. So delta by delta y is going to act on the 2x plus 3y to give us 3. And then we're going to subtract off delta by delta z is going to act on sine of xyz to give us xy cos of xyz. That's the I component done. Then we're going to go minus j. Well, I can imagine crossing out the column and the row that have the j in it. So now delta by delta x is going to act on the 2x plus 3y to give us 2. And then we're going to go minus delta by delta z is going to act on the xz cubed to give us 3xz squared. And then finally, we're going to go plus k times. Now we're just looking at this little 2x2 determinant here. So delta by delta x is going to act on the sine function to give us yz cos of xyz, and then that'll be minus, well, when delta by delta y acts on xz cubed, we're going to get 0 because there's no y in there. So that's that. So that gives us our curl. And if we want, we can write that back in component notation. That's totally optional. It's just a notational thing. If you are doing that, just watch the signs on the j term. So it would be 3xz squared minus 2. So either of those are good for our final answer. So main takeaway here is that when you're calculating the divergence, as we did up here, your answer is going to be some sort of function. It's going to be a bunch of terms added together. Whereas when you calculate the curl of your vector field, your answer is going to be in the form of a vector. And we're going to talk about the physical interpretation of divergence and curl right away. To understand the physical interpretation of divergence and curl, let's imagine that our vector field F represents a fluid flow. Let's say someone tells us that the divergence of our vector field at a certain point, xyz, is a positive number. Okay, so divergence of our vector field gives us a function, but if we then plug in specific coordinates, you'd be getting a number. So divergence evaluated at a certain point is going to be a number. Let's say someone tells us this number is positive. What that means is that there is net outflow at that point. So let's imagine our fluid flow in space. Let's imagine we're talking about this point right here. And we're going to talk about all the fluid that's flowing in and out of that point. So it's possible there might be a little bit of fluid, flowing in towards that point, but there's going to be more outflow than inflow. So here I'm just letting the length of the vectors just indicate, say, the density times the speed. So you've got a little bit of inflow, but more outflow, meaning net outflow at that point. If the divergence were negative at a certain point, then this would reverse and you would have net inflow at that point. And if the divergence of our vector field at a certain point were 0, that would tell us we would have outflow exactly equal to inflow at that point. So what the divergence is doing, it's giving us a function that we can then evaluate at any point in space. And by plugging different xyz coordinates in there, we get different numbers. Sometimes it'll be positive, sometimes it'll be negative, sometimes it'll be 0. And that's giving us an indication of whether we have net outflow, net inflow, or whether those are balanced at our point. So let's say that the divergence of our vector field is identically equal to 0. So when you see this triple line here, that means identically equal to, or in other words, equal 0 at all points. So if you calculated your divergence function and it were just equal to 0, no matter what your point was, then you'd say divergence of F identically equal to 0. Then the fluid is called incompressible. Now let's talk about the physical interpretation of the curl. So let's imagine that we're in 3D space. We've got this fluid flow happening. So I'm just going to draw some wavy stuff going on like this. And imagine that you've got a little ball, tiny little ball, sitting somewhere in this fluid flow. Let's imagine that this ball is being held in place by a magnet. So it's not moving with the fluid flow, but it is spinning on its own axis. So we've got this tiny ball spinning on its own axis based on the fluid flow. Well, a couple of physical questions we would ask then. We would want to get a sense of let's say the angular speed at which that ball is spinning, and we would want to make sense of the axis of rotation as well. And it turns out that both of these things are related to the curl. So if you actually double the angular speed of that ball, that gives you the magnitude of the curl vector. In case you're wondering why it's 2 times the angular speed, I'll just give you a really quick explanation for that. So if we scroll back to our curl example, basically when you calculate curl, every time you do that, there are going to be a couple of different terms coming up in each of your vector components. And because there are 2 different terms that are coming up, you're actually getting 2 times the angular speed. So that's just a very rough explanation without going through too much detail as to why you're actually getting double the angular speed. So magnitude of the curl vector, double your angular speed. And if you look at the direction of your curl vector, that's giving you your axis of rotation. So let's talk about that in a little bit more detail. Let's say our ball is spinning on its axis in 3D with a spin that's looking like that. Okay, so our curl vector would be going this way. So the curl vector is perpendicular to the plane in which that rotation is happening, and then the direction of the curl F is given by the right hand rule. So if you take your right hand and you just let your fingers curl in the direction of that spin, then your thumb is roughly going to point in the direction of curl F. So that's enough to help us realize that curl F is going to be going sort of up and to the right in this picture. Curl F is certainly not going to be going this way, according to the right hand rule. So when you calculate the curl, you're getting this vector that has variables x, y, z in it. And then you can plug in any coordinate that you like. So you can focus in on any point in space. You could look at, say, this point in space, or that point in space, or that point in space. And as you plug in your coordinates, what you're doing is you're imagining this idea of placing a tiny ball at that location, letting that ball spin on its own axis based on the fluid flow that's happening. And then the magnitude of the curl giving you double your angular speed, and the direction of the curl giving you your axis of rotation. So curl gives you complete information about the way that ball would spin. And that's talking about the micro rotation of the fluid that's happening around that point. Now, sometimes you might see a situation where you calculate the curl of F and it just comes out perfectly to the zero vector. When we say curl of F is identically equal to zero, we mean it comes out to the zero vector at every single point. So no matter what coordinates x, y, z you plug in here, you're getting the zero vector. So if that happens, then we say that the fluid is irrotational. So meaning there's no micro rotation around any of the points anywhere in space. Then last thing we'll talk about here are just the units. So let's go back to our fluid flow example. Let's say that our vector field is actually density times velocity. Let's say we're doing this in 3D. So we said that the units of F, units of our vector field, would be kilograms per meter squared second. And if we want to talk about the units of either the divergence of F or the curl of F, well, whether we're talking about divergence or whether we're talking about curl, what has happened mathematically is that we've taken partial derivatives with respect to x, y, or z of some of the components of our vector field. And taking that partial derivative just introduces another factor of meters in the denominator. So our units are going to be kilogram per meter cubed second. So that's all about divergence and curl. We know how to calculate divergence and curl based on these examples, and hopefully we also understand the physical interpretation of those two operations. Thanks for watching.